Hello students, welcome back to our science video. For today's lesson, our topic is about mechanical energy. At the end of this video, learners are expected to define and derive the formula for kinetic, potential, and mechanical energy. Work. When you move an object like a box, a net external force is needed. From Newton's second law of motion, a net external force is needed for a box to accelerate. Recall also that when the force causes the box to move parallel to the direction of force, work is done on the box. A net external force is needed to accelerate the box. Since the force causes the box to move along the direction of the force, work is also done. Will you be able to move the box if you are hungry? When you were successful in moving the box, where does the energy you spent in moving the box go? If you're hungry, you will not be able to push the box. You need some energy to move it. The energy you use to move the box is transferred to the box. During the movement of the box possesses kinetic energy. Kinetic energy is present in all moving objects. Work and kinetic energy. Consider a ball with an initial speed at position x. If the ball is pushed with an amount of force to a certain distance, the ball moves to a final position. Since a certain amount of force is applied to the ball will accelerate. Recall that the change in velocity per change in time is equal to acceleration. Mathematically, Newton's second law of motion can be expressed as F is equal to m times a, where F is the force acting on an object in Newton, m is the mass of the object in kilograms, and a is the object's acceleration in meters per second squared. When you push the ball, work is done because the amount of force has a direction similar to the direction of the movement of the ball. Mathematically, work is expressed as W is equal to F times D, where W is the work done in joules, F is the force in Newton, and D is the displacement in meters. If we substitute force from Newton's second law of motion to the formula for work, work is equal to mass times acceleration times displacement. Since the ball accelerated from an initial velocity to a final velocity, covering a distance, you can apply an uniformly accelerated motion equation given as acceleration is equal to final velocity squared minus initial velocity squared over 2 times displacement. Inserting this UAM equation into our working equation, you will have work is equal to mass times final velocity squared minus initial velocity squared over 2. Further simplification will yield work is equal to mass times final velocity squared over 2 minus mass times initial velocity squared over 2. The two terms are equivalent to an object's kinetic energy. Thus, kinetic energy is expressed as Ke is equal to 1/2 mv squared, where Ke is the kinetic energy of the objects measured in joules, m is the mass of the objects in kilograms, and v is the velocity of the object in meters per second. The equation derived earlier can be expressed in terms of kinetic energy. Hence, work is equal to final kinetic energy minus initial kinetic energy. Work and potential energy. Consider a ball lifted upwards to a given height by a basketball player from an initial position to a final position. To lift the ball upwards, the player must exert an upward force equal to its weight, which is equivalent to m times g. The applied force is equivalent to the ball's weight. The weight of the ball is equal to the product of the ball's mass and acceleration due to gravity. Mathematically, force is equal to mass times gravity, or m times g. If we substitute the ball's weight as the applied force to the formula for work, work is equal to mass times gravity times distance. Since the distance is also equal to the vertical distance h, we could replace the variable from d to h and get work is equal to mass times gravity times height. Mechanical energy is the sum of the potential and kinetic energy of an object. The total energy of the system is also equal to the mechanical energy. Let's apply the equation in a sample problem. How much energy is present in a falling object if it has a potential energy of 170 joules and kinetic energy of 350 joules? To answer the sample problem, let's follow these steps. Step 1. Identify what is required to find in the problem. You are asked to calculate the amount of energy present in the falling object. Step 2. Identify the given in the problem. The potential energy and kinetic energy of the falling object is given. Potential energy is equal to 170 joules, while kinetic energy is equal to 350 joules. Step 3. Write the working equation. Mechanical energy is equal to kinetic energy plus potential energy. Step 4. Substitute the given values. Mechanical energy is equal to 170 joules plus 350 joules. Step 5. Find the answer. Mechanical energy is equal to 520 joules. To summarize, work done on an object causes a change in its kinetic energy. Kinetic energy may be expressed as the half of the product between the object's mass and the square of its velocity. The kinetic energy of an object is always expressed in joules. Work done relative to a body's position involves gravitational potential energy, or simply potential energy. Potential energy may be expressed as the product of the object's mass, acceleration due to gravity, and the height where the object is situated. The potential energy of the object is always expressed in joules. Mechanical energy is the sum of the potential energy and kinetic energy acting simultaneously on a body. Thank you for watching. Do not forget to subscribe for more science educational videos by clicking the notification bell.